There is a relationship between conservative force and potential energy, and this is very useful that you can use to define the force from the potential energy. For a conservative force, we have that the work from the internal force is equal to the integral from Ri to Rf of the internal force dot dr. We will look at the easiest case in one dimension first, that is in one dimension. Work done by the internal force is equal to the integral from xi to xf of the f dx, which of course equal to the minus of the change of the potential energy. Okay. Now, if we look at a very small displacement delta x, since the integral is just a summation, as I explained before, so if we look just for a small segment of displacement delta x, the integral becomes just one segment of the summation. So we have that the small portion of the internal work, the work from the internal force, is approximately equal to the Fx delta x, which is equal to the delta U. I use this symbol delta U to tell you that this is also the change in the potential energy, but this is a change from the small displacement. Okay, maybe it's more proper to use the same notation for the work too. This means that this is the work from the very small displacement delta x, and I change the notation for the delta x too. Can have this as the delta x, make it the same. This symbol is a delta, but the small delta. The triangle is a big delta. Okay. So from this relation we have that Fx is equal to the minus of delta U over delta x, and in the limit of delta x go to 0, we have that F x is equal to the minus of du by dx. So this is a relation between the conservative force and the potential energy. The relation between the conservative force and the potential energy. And we can see this from the gravitational potential and the elastic potential. We have that Fg is equal to the minus mg. Remember that we use the upward vertical as a positive direction, so we have the minus I here. Okay, and this is equal to the minus of dug by dx, or we can say dy. It's just the symbol. And this is the minus of dmgy by dy. So you can see that the minus of dmgy by dy is equal to the minus of mg. Okay, so we have this relation between the gravitational force and the potential. We also have for the force from the spring, which is equal to the minus of kx, and is equal to the minus of dus by dx, which is equal to the minus of d by dx of half of the kx squared. And if you perform the derivative here, you can see that the d by dx of the half of kx squared is equal to the minus kx. So we have the relation between the potential energy and the conservative force. In general, (3D) case, we have that the conservative force can be expressed in terms of the potential energy as I of du by dx plus j of du by dy plus k of du by dc. Or we can write in the short-term notation as del of u. This notation, upside down triangle and have the arrow above, is defined as the I of d by dx and plus j d by dy and plus k d by dc. We call this the gradient operation, or the gradient of the function u. This is the gradient of the function u. It is a vector operator. That is, if you apply this operator to the function u, it means that you apply this derivative to u, this derivative to u, and this derivative to u, and get this expression. Okay, and that is the relation between the conservative force and the potential energy in general TD case.